Hello everyone. I will present the paper named Stream Query Denoising for Vectorized HD map construction. HD map serves the crucial purpose of furnishing centimeter-level location information for map elements and plays a pivotal role for various applications with autonomous driving. Great progress has been made in HD map construction. Typically, MapTR adopts an end-to-end approach to construct vectorized maps akin to the DTR paradigm. Nevertheless, the previous methods overlook the incorporation of temporal information. Although the efficiency of propagating sparse queries from the previous frame to the current frame has been demonstrated in Sandy object detection, the direct application of the previous temporal methods is not warranted due to the inherent modeling variability between curves and bounding boxes. Figure A and B illustrate the curves before and after transformation, respectively. And the purple segment in B shows that a number of different points are transformed to almost the same position due to the alterations in the perceptual range between the two frames. As shown in figure B and C, points within the orange dotted box must assimilate different biases despite orientating from nearly the same boundary. At the same time, the gray dotted box signifies the newly added part of the curve, necessitating all points along the entire line to acquire distinct offsides to accommodate the curve's growth. Therefore, the learning of temporal information can be viewed as a denoising process. As shown in the figure, the dark green curves indicate the ground truth of the previous frame warped to the current frame through the equal motion, and the light green curves represent the ground truth of the current frame. It can be seen that the position of sides within adjacent frames are different for curves of different shapes and positions. In addition, points on a curve have different deviations compared to the corresponding ground truth due to their different positions. Therefore, the position of sides from the temporal perspective can be regarded as the stream noise. As mentioned above, there exists the stream noise in the temporal propagation of map elements. Performing the denoising process on stream noise can help the model learn the temporal consistency of more map elements. To facilitate the learning of temporal consistency, we propose stream query denoising. To acquire an explicit one-to-one correspondence between previous ground truths and current ground truths, we propose adaptive temporal matching. First, we calculate the chamfer distance of gt and gt-1, and then we get the adaptive threshold according to the scale of gt. When the chamfer distance is smaller than the bar threshold, then both of them satisfy the temporal matching relationship. When transforming ground truth of previous frame to current frame based on equal motion, the stream noise for different instances has no significant change. The small variance may easily lead the model to overfitting. Hence, we propose dynamic curve noising. Concretely, we first decay the noise of the curve dynamically. Then we encode the categories and points of the curve separated. And finally, fuse two parts of information through MLP to obtain noise inquiries. We first compare SQD MapNet with previous competitive methods on the nuisance validation side for both 30-meter and 50-meter perception ranges. SQD MapNet outperforms other methods and tool sightings. We also gauge SQD map on another dataset, Agarverse 2. SQD MapNet consistency outperforms 3 MapNet by about 2 MAP, and the 30-meter and 50-meter range, validating the generalization and superiority of our approach. We show some quantitative comparisons with the static baseline stream MapNet and SQD MapNet in the figure. We can find that the static baseline and stream MapNet easily fail to recognize some curves in both simple and complex sentences compared to other methods. Executing map 9 achieves the temporal consistency effectively. That's all, thank you.